Have you ever wondered how rocks can melt deep within the earth without getting any hotter? It seems counterintuitive, doesn't it, to think of melting happening under cooler conditions, yet it is a fundamental process shaping our planet. Decompression melting is the process where hot, solid rock melts spontaneously as it moves upwards and the pressure on it decreases. This happens without any additional increase in temperature, simply because the rock crosses its melting point at lower pressures. The core mechanism behind this phenomenon lies in the relationship between pressure and a material's melting point. Think of how boiling water at sea level requires 100 degrees Celsius, but at a high altitude, water boils at a lower temperature because the atmospheric pressure is reduced. Rocks behave similarly. As solid rock deep within the earth experiences immense pressure, its melting point is elevated. However, if this hot, solid rock is brought closer to the surface through convection currents, the confining pressure on it lessens. When the pressure drops sufficiently, the rock's melting point decreases, allowing it to transition from a solid to a liquid state even though its temperature has not changed. This process is incredibly important for understanding plate tectonics, particularly at divergent plate boundaries like mid-ocean ridges. Here, mantle material rises to fill the gap created by separating plates. As this material ascends, the pressure on it decreases, leading to widespread decompression melting. The resulting magma, a molten mixture of rock-forming minerals, then erupts to form new oceanic crust. It also occurs at hot spots, like beneath Hawaii, where a plume of hot mantle rock rises from deep within the earth, undergoing the same pressure reduction and subsequent melting. A key takeaway here is the concept of a geotherm, which is the gradient of temperature through the Earth's interior. When the Earth's geotherm intersects the solidus, which is the line on a phase diagram representing the onset of melting for a rock at various pressures, melting begins. Decompression melting happens when the geotherm crosses the solidus at shallower depths due to a decrease in confining pressure, rather than an increase in temperature, creating vast volumes of magma that contribute to volcanism and crustal formation. This is a primary driver of volcanism in many tectonic settings. Understanding decompression melting is crucial because it explains how large volumes of magma are generated in the Earth, directly influencing the formation of new crust, the existence of volcanic islands, and the dynamics of plate movement. It highlights that melting is not always about adding heat, but often about removing pressure, a testament to the complex interplay of physics deep within our planet.